Well, howdy, physics, loose and inquisitive souls. Welcome again to Dynamic Gravity. Um, I haven't posted in a few months. I noticed some problems with the math that I had developed, and I had to really sort those out and just put the final nail in the coffin with this math. Either prove that this math that I devised to explain my formula was incorrect, and move on to another one, or figure something out if I can, or figure out what's going on here. And after a lot of work and going over, I think I've done that. I think the math now is pretty much complete for this this theory of gravity. And by the time you get done watching this video, you'll be able to calculate dark matter and dark energy throughout the entire universe. And successfully, have reasonable numbers that explain what we're observing. So, that's a tall order. That's a tall order. Let's dig into it. Let's see what we got here. All right. So let's go basic generality. This is Newton's equation for gravity that he created like 300 years ago. This is the equation of how gravity works. This is it. That he got it right 300 years ago. We're still using this to this day. A lot of people think like, oh, but Einstein, oh, he's so hot, he's so sexy, and his formula's so great. Dude, all his formula is trying to create a coordinate system in the form of metric tensors that basically account for variations in gravitational fields, like field strength, like traveling through the field, like what else? Speed, a bunch of things that he accounted for, and he created these metric tensors to do that. Excuse me, my brain damage is acting up from the war. But basically, when as complicated as this equation looks right here, when you're talking about regular velocities, regular gravitational field strength, just normal conditions, nothing like in a black hole or anything, this all reverts back to this. It's the same damn formula. It's just he created a coordinate system to account for these extra variables, but it is this. It is 100% this. It equates. This is half of it. The other half, I believe, is a Schwarzkopf metric. It just all reverts back to Newton when you're not talking about these extreme situations. So that is what it is. Now, my math, because my theory is based upon the ideology that gravity, what we perceive as gravity, is nothing more than the displacement of the electromagnetic force between the proton and the electron when the atoms are encroaching upon their individual spaces tighter they want to be from intense pressure, like something you find in the core of a celestial body or something. So it's only natural that this equation, Coulomb's law, which describes how the proton and the electron behave and play with each other, is going to be pivotal to my mathematics. And something you might want to notice, Newton's equation of gravity, Coulomb's equation, Newton, Coulomb. Boy, they sure do look a lot alike, don't they? Yeah, I wonder why that is. Probably because it's pretty much the same thing. So, Coulombs, yeah, here the Q stands for the charge of the particles, like the electron or proton. Excuse me, brain damage. So yeah, basically, the charge of a celestial body is going to be its gravitational accelerational strength. So like the Earth's gravity field is like 9.87 meters per second, meaning that's how fast something falls when it's in it. That's how strong its gravity is going to affect it. So that's what I use for Q. And I ended up getting, I guess we should probably go to the equations then so you guys can see the math. I know you want to see the math. You all want to see the math. Ooh, I just closed it out for 1 second. Give me about 5 seconds to sort this out, and I will have this totally good, I promise. Here we go. So, here is, let's go show formulas. Here is Coulomb. Here's Newton's equation of gravity. We could use Einstein's too. It's just so stupidly complicated. You have to have like supercomputers to calculate the whole concept of it. And like I said, at normal conditions, it just reverts back to Newton's anyways. So it's the same thing. Don't get all caught up on that Einstein did his whole new thing. He didn't. He stood atop of the shoulders of Newton, and that's how he got where he was at. Kudo to him, though. I don't think I'm hating on Einstein. He did a tremendous thing, but I think Newton was the OG, personally. But, okay, so here's the equation I devised. Pretty much same as Coulomb's law, only instead of Q charge, we're using gravitational acceleration. I call it gravity modifier G. So, I've calculated pretty much all of the modifier G's for every major celestial body and what it orbits in our solar system, and even the 4 stars closest to our sun, even our star with the galactic black hole, the Milky Way's black hole, and even our galactic black hole with Andromeda's black hole. Done a lot of calculations, a lot of math here. And at first, what first got me into this, thinking I was on the right track, is I was looking for equilibrium, right? Because my theory has a baked-in anti-gravity component. If 2 celestial bodies get too close to each other, they're going to start repelling on each other. And so when I originally calculated the mg, the modifier between the Earth and the Moon, I got like 0.96 or something. And I was like, hey, that's like 1. That's essentially what I'm looking for. That's perfect. But as I soon figured out, I had made an error in my math. I had this problem with the centrifugal force. Here I've calculated the centrifugal force. Here's all the newtons on all these objects are being exerted on them. You know, like the newtons on Mercury or Venus from the sun, you know, on the moon from the Earth, whatever. And here's the centrifugal force that they are generating, that they're going against gravity as they're orbiting their parent celestial body. And as you can see, when I calculate centrifugal force, once I accounted for this, I realized there was a huge problem with my math. Because it was like, if this is 1 and it's saying it's an equilibrium without even accounting for the centrifugal force, then it's way off, because centrifugal force is almost like identical to the force of gravity on it. I mean, in most cases, centrifugal force is a little bit less than the gravitational force, which is great, because my theory loves that, because here is my modifier. After I corrected the math, I found out my error was I was calculating the r squared fall off in kilometers, because they were using kilograms for the unit of mass. I'm like, kilograms, kilometers. No, That's not how it works. It's kilograms with meters. So this pushed my math back. The numbers I was getting back a lot further. And as you can see, I'm not sure if this number's right. That might be a little off, but basically, it's pretty small. And you take this modifier here that I calculated, and you times it by the force of newtons that Newton gets, or Einstein gets, if you want to get technical. And then that will give you the anti-gravity component, which I have here baked in. This dE is the distance equilibrium for whatever celestial objects I'm calculating, where the modifier becomes 1. So that's telling me when the modifier becomes 1, that is the point where the anti-gravity is completely in equilibrium with the gravity, and it's in equilibrium. And if you go any closer, the anti-gravity is going to start overwhelming the gravity. If you go any further away, gravity is going to start overwhelming the anti-gravity. This is just how the formula and math works, and this is exactly how I needed it to work with my theory. So, like I said, I was very, very happy about when I dug into this math, because it really works. It plays so nice with my theory of gravity. It's perfect. So, and then this would be the force of newtons at equilibrium. Pretty sure that is. Yeah. Force newtons at equilibrium. Force, you know what? I forgot what that was one of the things I was playing around with. G is just the total gravitational accelerations on the two objects at whatever distance they're at. And centrifugal force, which I never totally finished calculating. I mean, I calculated it manually, but I never got the thing because I was too lazy to write in the velocities and link all the numbers into my spreadsheet as I should. So instead, I just did it once manually as I needed to. But, okay, so we have, for most objects, the force of newtons is so much, the centrifugal force of them orbiting around their parent, flinging them outward, is almost in equilibrium with the force of newtons. And you have my modifier adding a little bit anti-gravity, helping it keep it in equilibrium and push it in the right direction. And especially if it gets too close, then the modifier goes up drastically, and it starts pushing back a lot harder, which is, especially for elliptical orbits, which we know, pretty much rule the entire universe, that's going to keep elliptical orbits stable and steady. My theory of gravity, does that. That's how it says everything is orbiting itself and somehow in equilibrium and keeping it going. If you're going to believe, Newton or Einstein, you have to believe it was just random luck that all the objects are orbiting at just the exact speed they need to not go off into space and not crash into everything. It's just all luck. And I don't believe it's luck. I believe it's equilibrium. And my theory of gravity says that. And here we are. So I fixed the math, right? And, for all the objects I calculated thus far, it's coming out really good numbers. It's really making perfect sense. Everything is coming out exactly as it should. Finishing off where Einstein left off. But there is a problem. The whole reason why we believe that dark matter and dark energy exist is because gravity does not behave the way it does in super celestials, is what I call them. Super celestials are black holes, galactic black holes, even neutron stars. They're super celestials. Their gravity is so strong that it's manipulating the matter in a way that's unnatural. and it's they don't play by the rules. All right, it's like my theory of gravity predicts that two celestial bodies would never collide under normal circumstances. It would have to be some pretty radical event to make them collide. But there's evidence from LIGO that says that super celestials, black holes, and neutron stars are colliding sometimes. Like I said, I've just pretty much acknowledged that super celestials are different. They're super for a reason. They don't play by the same rules everybody else does. And this is what led me to my breakthrough on completely attributing all dark matter and dark energy with my math and my gravitational theory. So Newton, Einstein, every theory of gravity, they all have the same problem. Once you have a galactic black hole, especially in the equation, nothing adds up right. For some reason, the observations you're seeing coming from that galactic massive black hole are not adding up to the math of standard gravity like Newton or Einstein. And, you know, Mond came along modifying Newton's dynamics to try and fix this by like square rooting, all different stuff, and manipulating the math. And they can get the math to explain what they need if they manipulate it enough to where they don't need dark matter anymore. But they still can't deal with dark energy. There's nothing they can do with dark energy. They have no explanation why the universe is expanding. Even Einstein's general relativity can't tell you why the universe is expanding. It only says, space-time must be expanding. But why? Exactly. You don't know. Shut up. My theory tells you why, and it can calculate it. So let's go down here. Here is all the stuff I calculated between our sun and the closest stars, Alpha Centauri, blah, blah, blah. Here's our sun between our galactic black hole. Right. And here is our galactic black hole interacting with Andromeda's galactic black hole. And as you can see, the modifier is incredibly small. And the gravitational forces right here. This is basically telling you that, if you can read the math, that our sun is experiencing almost the exact same amount of gravitational force exerted on it from our galactic black hole as it is from all the stars nearby it, which we know common sense tells us this cannot be true, because there's no way a galactic black hole in the center of a galaxy, which the entire galaxy is orbiting at the same time in a nice, neat, sphere or whatever shape the galaxy is, all being held together by the mass of the galactic black hole. So the galactic black hole absolutely has to be a stronger force acting on all the stars than the stars feel from their neighbor stars. There's just no way it can be held together if it's not. It's impossible. So, the way that I came about fixing this was it hit me. Super celestials are going to super. You can't stop it. That's what makes them special. And the reason why is because, according to my theory of gravity, it's the electromagnetic force, right, being displaced out is what's actually creating gravity. Well, that force is going to be displaced out a whole lot stronger if you have a gravitational celestial body like a black hole that's so strong that it's ripping away the protons and the electrons from each other, and it's ripping the neutrons apart. A neutron is just nothing more than a proton that ate an electron. That's it. It's going to rip those apart too. And then you're going to be left with essentially a core, I believe, of protons and surrounded by a shell of electrons, and they're separated. And this is going to basically allow you to maximize the amount of encroachment that atoms or protons at this point, maybe even quarks. Who knows how deep this rabbit hole goes? We've never been able to look inside of a black hole before. We don't know what's going on. We can only guess, but we do know this. It's so strong that a regular atom cannot exist. It's going to be ripped to shreds, and it's going to exist in its component parts somehow, or a plasma somehow. It's not going to be normal matter. That's 100% for sure. But right, so you got a black hole, and it's so strong it's ripping everything apart, and you have just like a mass of protons, and they're able to be squeezed a lot tighter than, say, a bunch of hydrogen atoms. And so that's going to encroach that electromagnetic force with all those protons, and it's going to push it out stronger, and you're going to have a stronger gravitational field. Now, as my theory says, there's a thing about this, though. We have this thing that Newton created, OG, called the gravitational constant. And it's believed by modern science that the gravitational constant is a constant throughout the universe. And it does not change. It does not matter how dense the matter is or how sparse it is. If you have this much matter, it's going to exert this much force, is what the gravitational constant says. Let's take a gander at this, right? So here we go. Here's the gravitational constant. So it's measured in these units. It's basically saying for every meter cubed that weighs 1 kilogram, I don't know, the S seconds, whatever, it's going to exert this much force of oh my God, I'm sorry. I'm not even showing you. Okay. Meters cubed for 1 kilogram of matter, it is going to exert this much force, which is a very, very small number, to the 11th power, negative 11th power. That 1 kilogram of matter is going to exert that much force. Now, it says that, it doesn't matter how sparsely density it is or how dense, it's going to always be the same. 1 kilogram exerts that much force. And when we calculate all these equations, we're just timesing the amount of mass by the gravitational constant. This much mass is going to exert this much force, and it falls off on this quickly. That's all the math is saying. That's it. Nothing more. So simple when you know what is going on. So, according to my theory, this number changes. And you might be like, wow, surely they would know that. You know what? I don't even know, man. I've been looking at it for years, trying to find out if this rules out my theory. I can't. I cannot find any experiment ever done to calculate the gravitational constant that didn't use lead as its source of gravity. And that's because lead is legit one of the most densest materials we have. It's like this close to being gold, and it's cheap. You can get a lot of it, so when you're making an experiment, you can afford it. You can make it affordable. If you do it all gold or something, it's going to cost you tens of millions of dollars, for what would cost you like a few thousand in lead. No one's going to do that. But even still, even though they're using all lead, you can see there's a problem with the gravitational constant. And this is a known problem in physics. It's not like any serious business can be like, there's no problem with the gravitational constant. No, there's a problem, dude. Every time they do the experiment, they get a different result. Now, granted, here, a lot of them got along this line, which is impressive, but maybe they just use the same quality lead with, amount of purities. Who knows? Maybe these guys use a little bit more, maybe these guys use a little bit less. They're pretty scattered, and for a gravitational constant, that is not what you want to see. It's not for any constant. You don't want to see it being bounced all over the scale depending on who does the experiment and where. That's not a constant, bro. So I'm thinking that when you have normal matter under normal compression, like you would find in iron, lead, maybe even gold, whatever, for the most part, the electromagnetic force is going to be displaced pretty similarly, within maybe, I don't know, a few percentile is what they're getting here. And they're just all using lead. I bet if they, did this experiment with wood, they would get totally different numbers. And physics acknowledges, they say this experiment can only be done in so many ways because it's such a small number you're trying to find that if you don't do everything just properly with like the right amount of everything, like lead, you're not going to get anything close to the right number. Almost proves my theory for me, doesn't it? Interesting. So the question is the gravitational constant constant? My theory says not so much. Mainstream physics says it absolutely is. But they can't explain dark energy and dark matter. We're getting to that. We're almost there. So we've got the gravitational constant right here in my spreadsheet. And if you notice, we go to Newton. Here we go. Gravitational constant is all up involved in that. When you calculate the gravitational acceleration of anything, you need the gravitational constant. You're just timesing the it's just half of Newton's theory. That's all it is, and you get the strength of gravity. You're just timesing it by the amount of mass and dividing it by the r squared fall off, and that gives you g, the gravitational acceleration, which you see for the Earth is 9.807. Jupiter's 24.79, all these things. Okay, let's say my theory is correct, right? Now, let's say we want to completely account for all dark energy using my math, using this new knowledge that the gravitational constant is not constant when you're talking about super celestials, especially. To what degree do we need the gravitational constant to change to get the numbers we want? Well, as it turns out, here is like it was somewhere like around there. Yeah, I messed up this math. But anyways, let's say it's normally negative 20, right? The modifier, the gravity modifier. We need it to be greater than 1 if we're going to have two galactic black hole cores interacting with each other and having enough pushback on each other that they're going to be expanding away, hence creating the expanding universe that we know that we're living in. And that would totally explain it, right? If the black hole starts off and just keeps eating and eating and eating, and it gets bigger and bigger and bigger, after a certain point, its gravitational strength gets so strong and its anti-gravity effect gets so strong that it's pushing back even on all the closest galaxies near it, on those black holes too. So to what degree do we have to add? How many zeros do we have to add to this? And as it turns out, I believe the answer is about 5 or 10. Is it 5? Yeah, it's 10. We got to add 10 zeros to get to the point where we are positive. We are now at 9 zeros, I believe. Here's the 10th one for both the gravitational acceleration for G1 and G2, which is Milky Way black hole, Andromeda black hole. And then after 10 zeros, 10 factors over, factor of 10, whatever, we are now positive mg, which is what we need to be in an expanding universe. So this is how you do it. You have galactic black holes, especially that are condensing the matter down, breaking it apart to just protons and electrons, and maybe even quarks. And now you're getting to the point where the electromagnetic force is pushed out and the gravitational constant is more pushed over by 10 zeros. And now, when the gravitational constant is pushed over by 10 zeros, when you calculate gravitational strength, these now have the exact gravity you need to give you the exact calculations that give you the expanding universe we know we're living in. And you might say, okay, Sean, that explains dark energy. What about dark matter? All right. I've calculated dark matter here with our sun and its interactions with the Milky Way galactic black hole. Here's the modifier normally, negative 22 power, very small. But that's all right. That's just, that doesn't have to be positive because the galaxy is not expanding outward that we know of. So that number you don't want to be positive, which is not. But as you can see here, here's what you need to know. Here's the force of Newtons. They're acting on our sun by the Milky Way's galactic black hole. And here is the calculated force outward going, centripetal force, as the sun is orbiting around that galactic black hole. And as you can see, it's not even close. The amount of force needed to pull in this sun to keep it at a stable orbit is like 1,000 times too small. Maybe even more. Like 1,000 times, maybe 10,000 times. So that's like at least 5 zeros. But remember, the math we're going for is like 10 zeros. So if we calculate this, basically we have a lot more pulling strength of gravity holding the entire galaxy all the way out to the rim, more than enough gravity to pull the entire galaxy and hold it together in the shape that it's in, whether it's an elliptical galaxy, sombrero galaxy, I don't know, Hello Kitty galaxy, whatever. I'm sure they're all out there. You now have enough gravity to hold the entire galaxy together. And it's coincidentally the same order that you need to attribute for the dark energy of galaxies interacting between each other. So there you have it. I've just completely laid out over this last half hour how my math works and what we need to do, which assumptions that are based completely on my theory of gravity, no one else's, that it will only be found in my theory of gravity, that if they are true, then my math absolutely can calculate all dark energy and dark matter and the galaxy and universe everywhere. And it also holds true, when we're looking at the solar system scale. Like I said, everything looks beautiful. I'm just so happy with this math right now. I believe it's finally at the point after 25 years of working on this theory. I believe it's done. I believe I've gone as far down the rabbit hole as I can. Maybe if I get some really serious, forces of nature in the world of physics and mathematics, maybe there can be some new revelations that are made or some new additions or accounting for this or that or whatever. Well beyond just my level. I have a bachelor's degree in physics and science, or physics and math. I'm pretty knowledgeable on everything, but I ain't on that level. I'm not. Never have been, never will be. So we'll see. I'm going to keep fighting the good fight and trying to push this theory out to anybody that will listen. But I made this theory up like at least 20 years ago now, and I'm telling you, man, it's nobody cares. Nobody cares. All the people that you would think, and science, physicists, that are big names, whatever, that work on gravity, you would think they would care to at least listen to an ideal like mine, my theory. They can explain as much as they can. They don't. They're not interested. I had the guy that was working on WIMPs or whatever from Harvard, and I talked to him. And he just straight up looked me in the face and said, listen, your theory sounds great and all, but I have a vested interest for it not to be true because I just spent the last 20 years of my life developing this WIMPs theory, and you're out your mind if you think I'm going to drop that after that much time and just go with you. That was what he told me. And from everyone I've talked to, that pretty much be the consensus. They don't care about the truth. They just want to validate their existence and all the work they've done in their fields. And that's all it comes down to. That's what science is nowadays, unfortunately. So I'm going to keep pushing. I tried to publish, but I can't because I don't have a academic email address. I'm not associated in an academic institute, so I don't have the privilege to publish a peer-reviewed paper. Science, man. It's science. It's a pretty raw deal for anybody who's not in the N club. But I'm going to do whatever I can. I hope all this made sense to you. If you made it to the end, kudos to you. God bless. You'll see me again. I'll make a new video sometime soon, just pushing out the basics of my theory. But yep, I think I'm going to call it there. I think I'm going to call success until I see evidence to the contrary. And hopefully the alpha G experiment at CERN will prove me wrong and prove me right and Einstein wrong. But time reveals all, baby. Time does not know how to lie. And it takes her a long time to speak. But when she do, that's the way it do. So, adios. Y'all have a good one. I'll catch you on the flip side.
Like, subscribe, submit.